Sometimes we have masonry walls in buildings that are subjected to tensile stress. The reason can be different. Maybe the slab below of this wall is weaker. Maybe we have loading on the bottom slab. Can be different. Maybe different supports for the walls. The goal for this video is to show you how you can model such wall to exclude the tensile stress from it with nonlinear calculation. My name is Ivan Beleš and I am support engineer for SCIA and Idea Statica. Now we are in SCIA Engineer and I have prepared a very small model. What do we have here? We have one bottom slab, one top slab, concrete, and two concrete walls, and one masonry wall, which is connected with hinges to the concrete, not to introduce some bending moment accidentally. The supports are on the way that we have supported only vertical direction. You see the slab is connected with hinges and this one also. So we have the same stiffness and we will introduce the tension by this surface load on the bottom slab. It doesn't matter how it's done, if it's with different stiffness or different supports on loads. And I thought this is a very simple model. It's not the best realistic model, but it's simple. And we have only supports in Y direction and only one in X direction not to introduce some tension, some tension stresses in the slab. So it should be simple, and maybe I should also remove this X from the model to leave only Y, and generally I don't need both of these supports. This is enough if it's supported on the bottom side. Okay, run the calculation, look at the results and check if it's what we need. What do we have for load cases? I have only self-weight of the structure, then the 6 kilonewtons on the bottom, 6 kilonewton on the top will be calculated separately in two different combinations, and wall replacement load. I will create a simplified 2D model, and this is empty, it's only the load case. Check the combinations. I will prepare, so I can delete it. So I will prepare new envelope ultimate combination. Let's say bottom, C1 bottom, and what we have there? Self-weight, this 6 kilonewton on the bottom slab, not on the top slab, and the wall replacement load. I can keep it here because I will not introduce the load in this model. I will introduce it only in this simplified 2D model. We will create a simplified 2D model. And it's not an issue if I have combination with both of them because it's placed only in the smaller 2D model. And we don't need to change the combination to look at the results. So the calculation is done. We can look at the deformations from this one combination, and you see it's connected. It looks like a gap, but it's because this slab is bended in both directions. So you see it's connected here. So everything is connected. How do we know that's the tension there? We can look at the tension stresses or internal forces, but I can also introduce integration strip in this wall with the width of 1 meter, and it goes from the center to the center. I don't know if the direction matters. And I will want also to evaluate the bending moment on the bottom slab. So we can also introduce one 3-meter integration strip in this bottom slab. So we have prepared the results. Now I can go to internal forces. For this one, let's say current, we will keep our combination, and I want to see the axial forces. I have to activate this integration strip, and we see nice, we get tension in it. So this is what we want to see. And let's check the bending moment. Is 104 kilonewtons. So I don't have a pen, doesn't matter. 104 in linear model with tension. So if we exclude this tension, we should get more deformation. I want to have some comparison model, very simple, and usually engineers calculate it dozens of years with 2D models. So I will copy everything to this one and simply delete everything which is in 3D. So we have only 2D. But now we miss the wall. So I need some load as a replacement. Usually, if you calculate masonry walls, then engineers say this is a simple load. The masonry wall has a stiffness, but usually for 2D models, you cannot introduce this stiffness. So it's calculated like a load. We can go to loads. I select this wall replacement load. So we have this top, not bottom. So we have this bottom, we have sulfate, and we go to this wall replacement load. And this is a line load. We have integration strip, but I will need also one internal edge in this plate. Okay, it's here because I need to place the load on this internal line. I don't want to use free loads in this simple model. So minus 9.42, it's the weight of the load, and it's sitting on this line. So we have now replaced everything. We have already the combination with the sulfate, with the surface load, and with this wall replacement load, and this is not here. So we should get some comparable results. Okay, this is a standard message which you also get. What does it mean? We have edges, we have free edges which are not connected to some other structure, and we have hinges on them. That means this edge is completely free. SCIA Engineer will not calculate it. It will be automatically excluded from the model, but I will delete it. So I select both of these linear hinges and delete them. So now we should get calculation without messages. Still the linear calculation. We are still in the linear calculation. Compare the bending moments. I cannot compare the vertical because it's not there. I can go to internal forces, combination, bottom, integration strip, extreme values for member, F5, empty selection. I select both. So this one and this one, F5. So 167 would you get in a simplified model, which is standard conservative calculation. We will try to achieve this result in a 3D model. So what can we do? I can copy the full model to this third line grid, which I have already prepared. And usually the first approach what the people start is to use the pressure only 2D elements. but this is not the correct way for us. Why? Because we have masonry wall, and masonry wall is an orthotropic wall where the shear stiffness in the wall, this is for this deformation, is reduced standard to 1%. To 0.01, it's 1%, and the stiffness parameter is the small d33. This is the shear stiffness of the wall. This is reduced. If you used the compression only 2D members, then the solver is using also orthotropic properties to reduce the stiffness in the main tension in the main direction of the main axial forces, and then it's done with orthotropic properties for each element, and this is a collision with our orthotropic properties which we want to introduce for the wall, and they will be rewritten, so we cannot use both in the same model. Therefore, this is not the right way for us. What we can use are nonlinear line hinges. So we need nonlinear calculation. I go to project settings. We have nonlinearity. You see, it's everything deactivated for this model. And we need beam local nonlinearity. It's also for 2D hinges. It's for beam hinges, but also for these line hinges. It's valid. You don't need to search special functionality for 2D nonlinearity. And we will not use this compression only 2D members. And now I can select the hinges. We have the directions, and this is our wall. The standard local coordinate system is X and Y. The line has also his own local coordinate system. You cannot see it, but it's there. The X is the line. The Y direction is in the plane. And Z is perpendicular. So if I move it, I think it goes in this direction. In this. So this should be the Z. It's only rotated. So we need to exclude tension in the Y direction. The nonlinear hinges has U plus and minus, and has force, let's say plus and minus. What we need, if we get the tension, we should have no resistance, but deformation. Let's say red. This should be the line. If we have compression, we should get resistance and no deformation. So no deformation, but resistance. This should be our line. You can draw really a polygon line if you want to create some sophisticated nonlinear hinges. There is only one thing you have to remember. It's forbidden to use horizontal and vertical lines, because some of this convergence of these nonlinear models, you need to introduce some small neglection. So if you have two deformations with the same resistance, then add some 1 Newton or on the second place after the comma, some difference to get a little bit neglected line, not horizontal, not vertical. If you do it wrong, you get an error message. It's not an issue. You get an error message, you can correct it. So how can we do it? This is the Y direction. We need a nonlinear hinge. Also, nonlinear hinge needs linear stiffness, because we will not perform only nonlinear calculation, we will run also the linear calculation, and the linear calculation cannot use our nonlinear function. This needs the linear stiffness, and also the nonlinear calculation needs the first iteration where this linear stiffness is used. I hope it's understandable. So we need, and usually I select some higher stiffness because in the worst case, it simply don't move. It's better it's not moved, as you get higher deformation for the first iteration, and then the engineer need to go back with the deformations on our line. So better you start with higher stiffness. And we need some stiffness. I create a new one. Let's say wall nonlinear. I will not create some curve because it's not necessary. We need only for positive axis, which is our tension, it should be free. And for negative axis, for compression, it should be rigid. That's all what you need for this simple hinge. They are already predefined. If you use it, you can use them, and you can also load it from the system database. But I wanted to create it extra. So this is our hinge. I will delete all these non-necessary hinges. This one and this one also. So we have only one nonlinear wall. Okay, it's there. We need for the nonlinear calculation nonlinear combinations. Nonlinear combinations. For the bottom, I have already its ultimate, all factors 1, that we can compare the results with the linear calculation, self-weight, this bottom surface load, and the wall replacement load. Wall replacement load is not issue here because it's not there. It's not there, it's only sitting here, so this will not influence our results. And to compare the results, also for the surface load on the top, then we should get only pressure. Okay. Run the calculation. Don't forget to activate the nonlinear calculation. Wait a little bit for the results. For a bigger models it could be longer. But this line hinges has also an advantage against the compression to the elements, because if you look at the results then or mesh, you will have a lot of finite elements, and this is an iterative calculation where SCIA Engineer has to turn off or make the element on the tension like a rubber, so very weak, and they get tension on this line and then more and more. So you need a lot of iterations because you have a lot of elements. But if you have line hinges, then you have maybe only 10 or 20 elements, so it's much quicker, the calculation, because all elements with tension are deactivated at once. So you get much less iterations. So it's calculated. We can compare the results. First, I would like to see the deformations. That's the first thing I want to see. You don't see this menu accidentally. Yesterday I have played with the configuration. I have deactivated and forgot to activate it again. So combination, nonlinear combination for the bottom. And check the results and look. And you see a gap here. Why? If we told it should sit on the wall, but we have the gap here. We have gap also here. That means there is somehow tension. But why? The reason is, you see it, if we use the top load, then it's connected because we load from the top. So this contact is working. It doesn't go through the slab. But why do we have tension? If we look on this bottom load, this is because this wall has reduced shear stiffness, but it has stiffness. Also, this 1% is enough to create a high member which has own stiffness, and it's not such weak that it's sitting on the plate. To compare the results, I need to make it a little bit weaker. So we can go to the properties, to the orthotropic properties, and reduce it to 0.1%. This is for this model. Usually this 1 to 10% should be enough, because the masonry wall is not completely weak. This is not only bricks placed one on the another. You have some glue or some mortar between them. So it has stiffness in the reality, but we don't want to have it in our model. Now compare the results for this bottom load. Okay, you see it's sitting on the wall, it's enough weak, and it's disconnected from the top wall. The top wall will not hold our wall on the top slab, or the top slab will not hold our wall, and it doesn't get tension. We can look at the internal forces. The vertical force, for example, in this integration strip, it's for current. We want to see the axial force. This is the linear combination, so nonlinear for bottom. So you see it's pressure. There is some under, it's 0. Okay. So we have only nice compression, only the self-weight is going down. We can compare the bending moments. It was 100, it was 167, I think. Should be also here. We look at the bending moments. So 167, 164. Of course, also this 0.1% is some stiffness, and it's reduced the bending moment. But you see, it's a result which can be compared. So we have no gap on the bottom, so the wall is nicely sitting on the bottom slab. We have gap on the top, it's disconnected. We have pressure only in the wall in the vertical direction, and we have bending moments which can be compared. So I hope this is what I wanted to explain. And that's all, I think. Thank you very much for your time, for watching, and maybe we see us at next video. Bye.